when we proposed to the NSF that they should give us a lot of money, one of the pitches that we made was we are not going to be 4 separate institutions, each with our own separate research agenda, doing our own thing, and occasionally writing annual reports talking about how much fun we're having talking together, but not actually doing it. We said, no, we're going to build a capstone project that's going to involve not necessarily all, but many of the threads, and certainly some threads from each institution, in pulling together a demo that will do something impressive. And the impressive thing that we proposed was to build a web server, which was to be verified from top to bottom. So one QED that says this piece of hardware running these bits is a web server in the sense of the RFCs. And we have been working hard on that. We do not have a web server to show you today, but we do have a server to show you today. And it is not verified with one QED absolutely from top to bottom, but a substantial part of it is verified across the Galena to C interface using both a whole bunch of technology that we've developed for specifying networked servers, mainly at Penn with a couple of people from Princeton and Yale, and also involving using VST to get all the way to C. So this is our current status report on our integrative capstone project. I want to say, before going on, that a lot of people have worked on this very hard. 3 people have worked especially hard, and they're all in the room. So I wonder if Li Yao and Nicholas and Yishuai would raise your hands or identify yourselves. Okay, I don't see Nicholas. He's probably resting. Anyway, these are the people that have really made it happen, and you should talk to them for all of the details. In particular, Li Yao has been the main one working on the high-level kind of infrastructure for how do we put together specifications of systems like this at the highest level. Yishuai has been the one involved in using that infrastructure for actually specifying a web server, which I won't talk about so much in this talk, but he can tell you. And Nicholas has been the one leading the effort to do the VST verification at the lower level of what I'll show you today. Okay. So the picture is we want this big stack of things with one QED that says the whole thing is correct. At the very top is a formal specification of concepts that you would read about in RFC documents describing the HTTP ecosystem. And then there's a web server written in C. It sits on top of the POSIX API for sockets and things like that, which is implemented by the Certicos hypervisor. It's running on top of a RISC-V chip specified at the ISA level, as usual, and that chip is going to be fabricated from code that Adam and his collaborators at MIT write. So the intention really is to go all the way from transistors to the network. So we've been working on this web server. Its design is loosely based on the GNU libmicroHTTP library. It is aimed at the moment at the embedded server ecosystem, which is actually quite an interesting area. There are a lot of bugs in embedded devices, like IoT devices, and a lot of the reasons for those bugs and vulnerabilities is that every internet-enabled light bulb that you can buy has a web server interface for configuring it, and those web servers are often quite vulnerable. So it would be nice to have a better story about that. We have a very basic web server implementation at the moment, written in C. We have a very basic web server specification written in Galena. And we're working on beefing both of those up and making them real. And I can tell you that they are real enough, they're not very real yet, but they're real enough that we can use the specification in a testing mode to actually find bugs in real deployed stock web servers. And that's a whole story that I'm not going to talk about today, but you can ask Yishuai about. I'm going to concentrate on a couple of questions today, because we only have an hour and a half, which is, and in fact, there will be 2 lectures on servers. I'm even going to concentrate on these questions, namely, what is the meta language like for writing down specifications? And I'll show you our current whack at that. And what do we need to do to test those specifications in a networked environment? And then the other question about integrating all of that with VST, Leonard is going to talk about on Friday. Okay, that is the last I will say in this talk about web servers, because web servers are pretty complicated beasts. And I want to be able to get into enough detail that I can give you a flavor of the way we actually do the proofs and testing. So I'm going to use a much smaller example, which we call a swap server. A swap server sits on the network like a web server, and it engages in the following interactions. So first of all, you connect to it in the usual way that you connect to a web server by opening a socket connection. You send it 1 byte. Actually, I think our actual swap server, we send 3 bytes at a time. But anyway, you send it a message, and it sends you back not the message you sent, but it sends you back its initial state, some constant that it was initialized with. Then somebody else comes along and connects to it again and sends a message, and it gets back the message that we sent the first time. And then the next one to connect would get back C, and so on. Okay, so it's a super simple server, but it does have some of the same interesting challenges as web servers. So it has to sit on the network. It has to accept connections over multiple sockets. And there's some state shared between those connections. So the fact that this one gets back 0 and this one gets back B, it models the fact that real web servers have databases behind them or file systems or whatever. They're stateful. Oops, sorry. Okay, so the picture of the world is we have an actual web server, or sorry, swap server written in C. It's not too long, but it's a few hundred lines long, because C is verbose. Then, as usual, as you've seen in the VST lectures, it's convenient to break up the proof into a couple of steps. Namely, we have the C implementation. We have a low-level implementation in Galena that uses functional data structures, and the control structure is maybe a little bit different from the concrete server, but it's rather similar to facilitate this proof of refinement in VST. And what I mean by refinement is every behavior of this is a behavior allowed by this. Then we have a high-level specification. You can think of it as a reference implementation. It's a very, very simple thing that shows the internals of what's supposed to be happening at a very high level. And we show that this Galena model refines the reference implementation in a slightly funny sense, which I'll come back to talking about in more detail, but we talk about refinement modulo the scrambling of messages that's going to happen on the network, because of course the actual implementation is going to be communicating with clients across a network and via an operating system on each side. And the communications, the interactions, can get scrambled by that process. So there are certain things like successive communications on a particular given connection that will stay in order, but communications on two different connections can be kind of arbitrarily scrambled. So we need a kind of special refinement relation. We can use not only Coq to prove this refinement relation, but also we can use QuickCheck to quickly test this correspondence between this kind of large and complicated implementation and this tiny, tiny reference implementation. And finally, we can test that the actual C code refines modulo what's happening on the network, refines our specification. Okay, so this is the big picture. The key notion that I'm going to have to explain to you, besides all of the kind of notations for setting all of this up, the key idea is this notion of descrambling what happens on the network. So why do we need to descramble things? Because this simple picture is often not what is observed on the client side. So what might actually happen is if several clients are talking to the server, that the messages involving the different connections happen at different times. They may be delayed on their way to the server, so the server may see them later than the client sent them. And once the server has seen them and responded, the responses may be delayed on their way back to the client. So the picture of the kind of testing framework is we have the server, we have a bunch of clients. This is the picture of the world in which the program is going to execute. So the program that we're trying to specify is the code running on the server. But the communications from these different clients can be interleaved, and the network can scramble them up even further. So how do we think about testing this thing? Well, we draw a box around all of the clients, and we say what we want to specify is the possible observations that can be made on sort of the union of all of the clients altogether. And we're going to demand that. So what we want is that every trace of events that can be observed over the network by a bunch of clients interacting with the real implementation is also a possible interaction that's allowed by the reference implementation. That is that's this notion of the real implementation refines the reference implementation modulo descrambling the scrambling that happened on the network. Okay, so that was the big picture. Let me give you a table of contents for the next hour and 10 minutes, unless there are any questions.
So scrambling sounds like reordering messages, but not dropping them or fabricating them or other phenomena.
Exactly. Well, yes, messages can be dropped in our notion of scrambling or indefinitely delayed, but not fabricating or doing malicious stuff like that. Okay, so here's the table of contents. So I am first going to walk you through the high-level structure of the proof that we are 99% finished with. So I'm going to show you the specification. I'm going to show you the intermediate C-level Galena implementation, and I'm going to show you the actual C implementation, not in very much detail. And then I'm going to show you the top-level theorem. And the top-level theorem has two parts. It says that the C-level Galena implementation refines the specification, and the C implementation refines the Galena's implementation. So the Galena implementation itself is not really important. Indeed, the top-level theorem existentially quantifies over it. So the top-level theorem really says there's some intermediate representation that is refined by the C and that refines the top-level specification. The first of these, I'm then going to try in the rest of this talk to give you a little bit more detailed sense of what it looks like, and Leonard will talk about the second on Friday. So what I will talk about is I'll first introduce the notion that we call interaction trees, which is our notation for writing down the abstract syntax of computations like behaviors of web servers. I will then talk some more about descrambling, and I'll wind up, if there's time, talking a bit more about how we test in this context. Okay, so now I need to switch to here. All right, is that font big enough for the back? Okay, so if you do a pull on the DSSS 18 repository and have a look in the DW directory, that's the deep web directory, because deep web, of course, is the name of our server, you will find in there a docs subdirectory, and that has, and this is the table of contents in that subdirectory. So we haven't prepared extensive homework exercises and things like that. If we had another month, maybe we would have. But for today, my goal is really just to give you a tour of this code and a sense of what's in there. You can look at it in detail yourself later on, but it's going to be a little bit of an impressionistic skim through quite a bit of code. So let's start with the spec. Here it is. So here is the whole specification, the top-level specification, or reference implementation, if you like. So the top-level spec consists of a call to the swap observer loop with a particular buffer size and a particular initial message. The initial message, I don't think we see it here, but I'll tell you for free, is the message 000. So that's what the first client is going to get back. And the guts of the server are this swap observer loop. Now, I'm going to come back to defining many of the words that we see here. So some of it is, or almost none of the details is going to make perfect sense, but just to get a sense of what the spec looks like. So first of all, this spec is a co-fixed point. A co-fixed point is part of Coq's co-induction features, which we aren't really telling you much about in these couple of weeks because the time is short. But for those of you that are not familiar with co-induction in Coq, for present purposes, you can think of this as just like a fixed point definition, except that we're going to allow it to have not only finite but also infinite behaviors. So it describes non-terminating computations that we can interact with. Okay, what are these interactions? So this swap observer loop takes as parameters a buffer size, a list of currently open connections, and an initial message, or the last message that we saw. And then what does it do? It chooses non-deterministically between two different things. So this